Hi everyone, Mrs. Basega here, and today we're going to work on conservation of momentum. After this lesson, you should be able to use conservation of momentum to calculate a final velocity, to draw a momentum bar graph, and to use a velocity versus time graph to interpret two objects interacting during a collision. You got all that? Okay, whenever I say conservation, I want you to think an exchange. Even though in normal parlance, conservation might mean to save, in physics parlance, I want you to think of conservation as saving. Now, when two objects make up a system, they can interchange things from one to the other. A closed system is where those two objects only interact with each other. Example, conservation of money. In this example, let's say I have $100 and me being very generous will lend my friend $80. This is an example of conservation of total money. The total money is $100. We exchange it between just the two of us, not my banker, not my mortgage payment, not my car payment, not right? Just the two of us exchange money for $100 total. You might remember conservation from chemistry as well. Maybe you've seen it as conservation of charge. When we do charge numerically later, charge is going to have the symbol Q. Get used to it. Charge is going to have the symbol Q. And in this case, the charges moving from the sweater to the balloon make the balloon negative. So the sweater is positive, and they're only exchanging electrons, between the sweater and balloon. That's a closed system. As a result of this interaction, the balloon gains electrons and becomes negative. The sweater loses electrons and becomes positive, but they're still neutrally charged because they only move the charges from one place to the other. Get it? Same with mass. When you did conservation of mass back in chemistry, you did things like taking chemicals out of a bottle. In this case, I take 140 something grams out of this bottle. Oh, maybe that's 0.14 something grams out of this bottle. And I can figure out how much total is left in the bottle because we're only exchanging mass between the bottle and the measuring plate. So now let's do this as conservation of momentum. Conservation of momentum is when two or more objects in a system only exchange momentum with each other. And how does one exchange momentum? Through an interaction. And whenever you see this word interaction here, I want you to think Newton's third law, interaction force pair. Big idea here. Because these spheres are only interacting with each other, momentum can only be transferred to adjacent spheres. That means the total of momentum will always stay the same in this system, which is why the spheres always have the same velocity after. So let's deal with this example. Let's say I have a 2 kilogram block traveling at 3 meters per second, hits a stationary 1 kilogram sphere, and after the collision, they stick together. This is called inelastic, and we'll get to it later. Let's say we want to find out the final velocity. This is our first objective of the day. Well, we can use conservation of momentum. That means the total momentum in the before picture is equal to the total momentum in the after picture. And how much momentum is in the before picture? Well, there's 6 in the red block and 0 in the blue sphere. There's 6 Newton seconds total. Okay, so afterwards, there still has to be 6 Newton seconds total momentum in the system. But I don't know the final velocity. So when I go calculate the total final momentum, I'm just going to leave v as v. I don't know what it is. It's a variable. I'm just going to leave it there. I'll deal with it later. So how many v terms do we have? Well, I have 2v there and 1v there. That means 3v total. So 6 Newton seconds split up over 3 kilograms of mass gives a velocity of 2 meters per second to the right. And if you're a steps solver, you like need to know the steps in order to do this. What I would do is I would take the word problem and number one, draw out a before and after diagram. I'm not talking about a free body diagram. I'm not talking about a graph. I want you to draw me a picture of each object with its mass and velocity labeled. If it's unknown, just label it V. Then take the momentum of each object in the system. That should give you enough information to solve the problem. Because in this case, I know the mass and velocity. I know the mass and velocity. I know the masses of my two objects at the end. And setting the before momentum equal to the after momentum is my last step. So in this case, 6 equals 3F, solve for V. Now, if you wanted to picture this as a momentum bar chart, well, momentum has to get transferred between my two objects, right? So pink has 6 Newton seconds to start. Blue has no momentum. As a result of this collision, blue gains momentum. How to figure out how much momentum it has? Well, blue is going to gain 2 meters per second times 1. Blue now has 2 Newton seconds of momentum, meaning red has to have 4. So 6 plus 0 equals 4 plus 2. We can do that. Conservation of momentum says that this normal force that occurred between the two objects in this collision, normal force, remember, prevents solid objects from going through each other. The normal force caused the blue sphere to gain momentum at the same rate that the red block lost momentum. Momentum got transferred from red to blue. So let's do another example. Let's say I have two objects that are moving to start. In this case, there's two football players head-on inelastic collision. They're going to stick together afterwards during this tackle, and we want to figure out where do they go and how fast do they go there. So find the final velocity. So I drew out my before and after diagram. I'm going to calculate the momentum. Red has a momentum of 360. Blue has a momentum of negative 300. Lots of people who got things wrong in the lab dropped negative signs for things moving to the left. So remember, negative left. And the final momentum, well, for this, I don't know what VF is, but I do know they have the same velocity. During this tackle, they stick together and move with the same final velocity. This means that 60 Newton seconds of total momentum is split up over 160 kilograms of mass, leaving a final velocity of 0.375 meters per second. I divide the 160 to the left to get my velocity. So let's deal with this in terms of an impulse momentum. Okay, after the collision, I labeled my velocity, and both of these objects are moving together at 0.375 meters per second to the right. That means afterwards, red has a momentum of only 22.5 Newton seconds. Red loses momentum in this collision. Blue is now going in the positive direction. It has gained positive momentum as a result of the normal force in this collision. So it's 100 kilograms moving at 0.375 meters per second. So the blue person has 37.5 Newton seconds of final momentum. If we want to look at this with impulse and momentum together, what I need to do is narrow my view. So I'm getting rid of blue. Bye. Let's look at red. How much impulse happened to red during this collision? I don't need the force times time. I don't need the area under the curve. But what I need to see is that the impulse caused it to lose momentum. Red loses momentum because of the impulse applied by blue through the normal force. Similarly, blue gained momentum. Where did blue get its momentum from? It gained it from red. The normal force of red during the collision caused blue's momentum to become positive. The normal force created an impulse which changed the momentum. So if I look at these two together, you'll notice that the impulse for red is negative because it lost momentum. The impulse for blue is positive because it gained momentum. But overall, the total amount of momentum stays the same. So one last example, and an example you don't want to do. Let's say I take a 0.5 kilogram ball and I throw it at 30 meters per second at a car, which by the way is super fast, like above 70 miles an hour. Okay? So I throw the ball at the car and it bounces right back at me at negative 25 meters per second, which is about 65 miles an hour. Hmm. So I draw out my before and after diagram, label all the masses and velocities I know, and I leave the final velocity of the car blank. I'm going to calculate the momentum before by taking the momentum of each object, ball, and car. I see there's only 15 newton seconds of momentum to start. But when the ball bounces backward, it actually has negative momentum. See that? When the ball bounces backward, it has negative momentum. So I actually need to add this negative 12.5 to the other side. And that means the velocity of the car is very, very slow. How do we depict this in a velocity versus time graph? You probably aren't asking yourself. You depict it like this. The ball has much, 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 much less mass. So the ball has this very large change in velocity. I obviously didn't draw this to scale. The ball has a very large change in velocity because the ball has less mass, less inertia. So it experiences the same force, but less mass, less inertia means it has a much higher acceleration. Whereas the car experiences the same force, but it has way more mass. So its acceleration is small and it barely changes velocity. So what I want you to do is I want you to use this video to help take notes. Make sure you've got notes on how to solve conservation of momentum. Go try the homework and I will see you tomorrow. Bye.